السلام عليكم ورحمة الله وبركاته. معكم مساكم الله بالخير. معكم نائب رئيس نادي الهندسة الكيميائية محمد المحاسن. رحب فيكم اليوم في محاضرتنا عن ال H2S، ومع مهندس أحمد. تفضل.
الله يعطيكم العافية. بس معليش سؤال بس. تبون المحاضرة تكون انجلش ولا عادي عربي؟
لا يريح. ما
اوكي خلاص. يعني بخليها انجلش وعربي في نفس الوقت، يعني مخلوط على حسب. يعطيكم العافية
تمام.
شباب. اتشرف في حضوري معكم اليوم. شكرا جزيلا على إتاحة هذه الفرصة. طبعا راح ابتدي بالتعريف بنفسي. اسمي أحمد السويج. I'm lead engineer managing the H2S lab in Baker Hughes. It is the only H2S lab owned by Surface Oil Company in the kingdom, so it is a unique capability. Let me just share screen. Okay, can you see my screen now?
Yes.
Okay, great. So I'll start by just answering the questions that you might be having in your mind. Why we care about H2S? Why do we have to know about H2S? What's the reason I'm trying to raise the awareness of you about H2S? And the answer to this question is, as you are going to be engineers and you will be working in different work sites, H2S, it's high. The probability of you having to deal with H2S is high because H2S can be found in different applications in different work sites. For example, you can see the H2S in petroleum industry, in mines, in manure beds, in many other industries. So if you are going to work as an engineer, you, the likelihood if you dealing with H2S is high. So in this case, it's a good practice to raise the awareness of H2S. As I'm coming from an oil and gas industry, I'll give more attention to oil and gas. So in our area of work, for example, if you look at the gas wells around the world, the distribution of gas wells around the world, you can see that 40% of gas wells located in this area, I mean in Saudi Arabia and Middle East. That's the good news. The bad news is more than 90% of those 40% coming with both corrosive gases, CO2 and H2S. Having these two gases inside the well put a lot of pressure on material, on metal, on elastomers, on non-metallic, and also specifically if we are talking about the H2S, it's put a lot of pressure on the HSE, the safety of the people working there. It's a big concern because of the H2S. So in order to deal with H2S or dealing with anything else, it's not specifically about H2S, we have to know about it. We have to know the properties of that thing before we deal with it. So let's start talking about the properties of the H2S. The H2S is extremely toxic colorless gas. So it can kill at relatively low concentration. It kills at ppm level. It doesn't need to go to percentage. At ppm level, it can kill. So it's this is something nobody can take lightly in the industry. At low concentration, below 100 ppm, it smells like rotten egg. However, if the concentration increase above the 100, it causes the olfactory nerve paralysis, which means you cannot smell it anymore. So in this case, you cannot rely on your nose to protect you from H2S, because if you cannot smell it anymore, it's either it's gone or it's reached a high level where you cannot smell it. Another part is the explosivity of the H2S. So whenever it has a good mixture with air between 4.6 and 46%, whenever there is a spark, it explodes, causing a lot of damage to properties, causing a lot of hazards to people working on that. And it's very corrosive. The metal in drilling, in production, for example, it's not necessarily talking about the oil and gas, but because I'm coming from that industry, so I'm keeping everything related to oil and gas. So it's corrosive to metal, to plastic, to elastomers. It put a lot of pressure on the material selection. It caused a lot of failure. The corrosion causing a lot of failures in oil and gas industry. Actually, more than 25% of failures of oil and gas industry is due to corrosion, and a big part of that due to H2S. It's very corrosive. So the H2S is relatively heavier than air, as the relative density is 1.18. So it's settled down when it's separate. The boiling point is very low, which means it is in gas phase under normal condition, and it's soluble in water and also in oil. And it causes corrosion because it's soluble. So as you know, the corrosion needs the three parts: the oxidants and the electrolyte and the metal. So when the gas dissolve in the water, it causes acid, and that increase the probability of corrosion. So as we know now, the properties of H2S, we know how dangerous it is. I just would like to walk you through the toxicology of the H2S. Those numbers are intimidating. Okay, so as you can see here, if we go from the bottom, as the concentration is going up and up, the consequences is getting more severe until it reach the 100 ppm, which is considered to be the IDLH, which is the immediate danger to life and health. Above that, the concentration causing a lot of health issue. As you can see here, if it goes above 1000, it causes nearly instant death. It's just 1000 ppm. So you can imagine how toxic this gas is. So it's how it works. Actually, it targets a specific organ in the body. The first targeted organ is respiratory system. It causes a condition called pulmonary edema. The pulmonary edema is a medical condition when the liquid accumulate in the lung, causing breathing difficulties, and in the severe cases, it can lead to death. And also, it's attack the central nervous system. It causes the neurobehavioral impairment, and it targets the eyes as well. It causes the irritation and tearing for the eyes. Okay, as we see now how bad that is in Baker. Before talking about Baker Hughes, there are many organizations in the US and in Europe which sets some limitation of the exposure. Let's start with the US. There is an organization which is the ACGIH, the American Conference of Governmental Industrial Hygienists. They set the threshold limit value to 1 ppm for 8 hours, sorry. So you cannot be exposed to more than 1 ppm in the 8 hours. If they're talking about the short-term exposure limit, it's 5 ppm. So they are very strict when it comes to H2S. There is another organization which is OSHA, Occupational Safety and Health Administration. It sets the permissible exposure limit to the time-weighted average. And what I mean by time-weighted average is that it allows for the concentration to go up and down during a day as long as the permissible exposure limit is not exceeded. So as long as we are not exceeding the 20 ppm, it's not okay. I'm not saying it's okay, but it's permissible to expose to less than 20 ppm for 8 hours. For the short term exposure limit, it's 50 ppm for 10 minutes. As you know, as you may know that for any chemical, it's about the duration and the concentration. So these two factors are playing role together for that. There is another organization which called NOISH, National Institute for Occupational Safety and Health. They states that the REL, which is the recommended exposure limit, is 10 ppm for 10 minutes only. And OSHA and NOISH stated that the immediate danger to life and health is 100 ppm. So when it goes to above 100, it's getting more serious. For the European Union, they stated that the permissible exposure limit on the time-weighted average is 5 ppm for 8 hours. And for the short-term exposure limit, it's 10 ppm for 15 minutes. So if someone is exposed to 10 ppm for 15 minutes, he is still safe, but not more than that. In Baker Hughes, we have 2 levels as we set in our lab. So in the low level alarm, so if we have like 3 ppm detected on any of our sensors distributed in our lab, it gives a local alarm, low level alarm. When it goes to 15 ppm, so that's the high level alarm, the full evacuation of the building. So we are taking that seriously based on the organization's recommendation. As we know now how dangerous this chemical is, we decided in Baker Hughes in our lab when we started the lab a few years back to the purpose of that lab is to reduce the total expense of corrosion by helping in recommending the material, helping in corrosion inhibitor recommendation. So to be used in many applications, in fluid, in elastomer. So when we started the lab, we decided that there will be no uncontrolled molecule of H2S gets left behind. So we need to control each single molecule of H2S. We don't allow any H2S to go uncontrolled. And to do that, we have set a lot of barriers. We have put a lot of sensors. We are controlling the lab remotely during the critical time, which means that during the open source when the H2S is flowing from one point to another. We have a lot of documentations to states how we handle the emergency situation, how to handle the H2S in normal operation. And we also have the emergency response team, which I will talk about in some details in a few minutes. So as a start to control the HSE in our lab, we go through the hierarchy of control. So we started with elimination of hazards when we have to physically remove the hazards. Unfortunately, as the H2S is always there. So whenever we are drilling, whenever we are producing, there will be an H2S. Our equipment, our people can be exposed to H2S, so we cannot eliminate that. So we go to the substitution to replace the hazard. I'll talk about it more in next slide. And then we go to the engineering, where we isolate people from the hazards through engineering, and the administrative, which is to change the way people work. It's either we change how we do things, or we write the procedure, or we train people. So all that fall under the administrative. And the least effective way of protection is the BBEs. So the BBEs is the last line of defense. So now, as I mentioned, for the elimination, there's nothing we could do about it. The H2S, we have to deal with it. So when we go to the substitution, as an example, we have done two substitution to the procedure. For example, we charge gas at low temperature. As we go to the high temperature, we charge the gas at high temperature. That increases the probability of having accidents, because temperature with gas flowing, that cause some risk. So what we do, we charge at low temperature, and then we heat the gas inside the pressure tested cell to reduce the probability of having any accidents. Another thing is we adjust the partial pressure. So for example, if you go and trying to simulate the downhole condition, for example, the pressure in the gas pressure is, for example, 5,000 psi, and it's the concentration of H2S or CO2 is like 5% or 10%. So we don't go to 5,000 psi. We use the partial pressure theory to adjust the pressure of the CO2 and H2S, because these are the two corrosive gases. Other gases are not contributing to the corrosion to the metal. For the engineering, we have a lot of approaches related to material. For example, we have chosen the material which can tolerate the H2S. We have different sensors distributed around the H2S lab and also the general lab. We are keeping the H2S cylinder inside a cabinet which is under vacuum. We have in-lab scrubber, and we have main scrubber. So we have a lot of engineering measures we have taken to protect ourselves. We always keep two different barriers between our lab workers and the H2S. For the administrative, we have written a lot of operating procedure. We have wrote how to do things, how to run a test, how to check for problems. We wrote the emergency response plan, the chemical hygiene plan, which the emergency response plan states everything we need to do in case of emergency, what we expect to do in case of emergency. For the chemical hygiene plan, it talks about the quality of everything we do in our lab. So the quality as well as safety. It's not quality alone. For the personal protection, we have badges. We are using the body system, so nobody wearing the SCBA, for example. If we are going to go and open the cylinder, the H2S cylinder, our lab workers have to wear the SCBA, the self-breathing protection apparatus. They have to wear it, and they have to have the badges to detect H2S. They have to have it, and we use the body system. So if someone is going inside wearing the SCBA to open the H2S or dealing with the H2S, he cannot go alone. He needs to go with someone else. And also we created the SCBA team, which is a team trained and certified by OSHA to deal with the H2S. So we trained that team to handle the H2S in case of emergency, in case if we have leak. They have to handle that. They are trained and certified, and I'll talk more about them when in next slide. So this is part of our engineering. It's we have modeled the ventilation efficiency of our H2S lab. So we go with the worst case scenario. If we have a cylinder, and by the way, we are limited with the amount of H2S we keep in our lab to 20 liters. So one cylinder is 10 liter, and let's assume that the whole cylinder, the valve just ruptured and it's released all the cylinder content inside the lab. It's unlikely to happen, but we wanted to check the efficiency of our ventilation. So in that case, the maximum concentration that will be found in our lab will be 73,000 ppm. And you can imagine how bad that is, because as we mentioned in the toxicology slide, that 1,000 is enough to kill someone instantly. So can you imagine if someone is inside and there is 37,000 ppm? However, the ventilation in our lab can drop that concentration within few minutes, within 7 minutes, to less than 100 ppm, which is the immediate danger to life and health. So that's ventilation system is so powerful. It reduces the concentration in very fast. So the engineering measure we are taking is working. So now in the emergency response, let's assume that a small part of H2S released from here on there, and it was detected by one of the sensors. So uh, the first, as I mentioned, it will go to low concentration, local buzz inside the lab. When it goes to the 15 ppm, it gives the local alarm, the full alarm, sorry, which means that the full lab and the whole building will be evacuated. And that's when the time the SCBA team is needed. So the first thing, in addition to the alarm, there are light towers at the lab, distributed at the lab at the building, so that the people can see and can figure out there is something, even if they couldn't hear. Let's assume that someone is putting his headphones and he couldn't hear the alarm. It's unlikely, but let's assume that he will be seeing the evacuation building, the red light here. So it's distributed around the lab. And when they are leaving, so they just go to the assembly point. We have two different assembly points here, and we educate people about the best route they need to go out of the building. And if you can see here, this is the security room, which we are using as the incident command post. What I mean by incident command post is the operation room for the SCBA team. So that room contains everything we might need to go inside and figure out what's going on and trying to fix the problem. So it has the cameras, it has the sensors readings, and also it has uh, uh, everything that you can see here. So we have the SCBA, we have the badges, we have the area monitors. So everything we might need to help our SCBA team to go inside and figure out what's the problem and tackle the problem is kept in our emergency room, which is the SCBA or the incident command post. I think I covered all the parts related to H2S in general and what we do in our lab to keep H2S under control. So hope that gives you an overview about the H2S and how to handle it, how we handle it. And if you have any question, I'll be glad to answer that. So thank you for listening. Ahmed, can you hear me?
Yes, I'm here.
Okay. So if you have any question.
Yes, Abdullah.
If I may be honest, Doctor, first of all, thank you for this interesting lecture. Second of all, I might be new to the major chemical engineering, but it seems like it's a great hassle to do to keep this a safe process to deal with H2S. Why do we keep using it if it's such a hassle to work with it?
Okay, that's a good question. Okay, so the answer to that question consists of two parts. The first part is H2S is always there, not always, but most probably there in the oil and gas industry. So when you drill a well, a gas well or oil well, it's always there. So H2S is always there. So we cannot avoid that. Okay, so that's the first part. The second part, in order to deal with the H2S in the field, we have to do some experiments in the lab to help, for example, in material selection, to help, for example, in elastomer selection. H2S is very corrosive. So if you are drilling or producing from a sour wells, and what I mean by sour, it has H2S. So your equipment can corrode in a short period of time. And if they corrode, leaks can happen. They need to be replaced. There is a cost for that. There is a hazard associated with that. So all that could be avoided by doing testing in the lab to give the recommendation to the field. And that's the reason why we have the lab in Baker Hughes, and we have to tolerate that hazard. Does that answer your question?
Yes, thank you very much, Doctor. That is a
No
precise
worries.
answer.
No worries.
في أحد بعد عنده سؤال؟ They are thanking you.
Okay, so no more questions?
No, I think. There is a question. Does the team contain process safety engineer?
Okay, that's good question as well. Okay, so the team, our team does not have, I'm talking about the team in our lab, okay, here in Saudi. However, we have a process safety engineer in Sugarland and in Kirby in UK. they helped us a lot to build the lab. So they were with us since the beginning. We visited their labs. We discussed with their subject matter expert. They visited us many times to review our lab. So we work with them. That's the first part. The second part, there is an engineer who joined us as an intern. He's really a great engineer. He joined us from KFUBM and worked for us for a few months as a process safety engineer, and he helped us a lot to improve the safety of our lab. So he has done a lot of modeling. He came up with a lot of assumptions. So he helped us a lot to improve the safety of our lab. In case we have any, let's say, for example, something new that we need to add, or we face any challenge, we include our expert from the different part of the company.
Also, how can we rate the quantity of H2S existed inside a wall?
Inside, sorry, can you repeat the question again?
How can we rate the quantity of H2S existed inside a wall or a well?
Oh, okay. So you mean inside the well, how to measure the H2S?
Yes.
By sampling. They take sample, and by analysis of that sample, they can know what's the content of that gas or that oil. So they take samples.
How can we avoid the corrosion being produced by H2S?
Okay, so that's I'll answer the question in general about the corrosion. The corrosion in general, we have different approaches. The first approach is either we go with the material selection. So there are some material which resist corrosion due to H2S. Okay, so it's either material selection or a corrosion inhibitor, which is a chemical injected to the well, and that chemical reduce the corrosion by forming a very thin layer on the material. Sometimes we have to change the condition, so it depends on the situation, but it's either the material or the chemical. So these are the main thing that we are looking at. Of course, we are looking at the efficiency. We are looking at the cost of the solution. So all those factors plays on what we call the integrity management to maintain the integrity of the material.
I have a question.
Go ahead.
You said that if an area or a lab was contaminated or a breach happened, and the H2S went out of the system, the first is always the first option for it, the ventilation, or there are more preferable options to deal with it?
It is the ventilation. The first thing is the ventilation, because the ventilation just suck the air through the main duct to the main scrubber at the back of the building. And that scrubber is equipped with H2S scavenger, which scavenge the H2S and send the other gases to atmosphere. So in our lab, if something leaked, the ventilation, the fume hood sucked the H2S, and it passes it through 2 beds of H2S scavenger, which scavenge the H2S. Now, H2S scavenger keep the H2S inside. It react with H2S and keep it inside the scrubber. And after a certain period of time, we replace that scavenger.
Thank you. Yeah, that answers my question.
Great.
There is a question. No insulator have been found for H2S to be used by the equipment to not be damaged.
Sorry, what's the question again?
Is there an insulator have been found for H2S to be used for reduce the damage?
Okay, so you mean that material which resist the corrosion of H2S, right? Is that what you mean?
Yes.
Okay. There are material which resist H2S. However, each material has limitation. Okay, so there is no material which does not corrode by H2S in general. There are some material resist corrosion of H2S under certain condition. So, for example, if we take a material which resists H2S at a temperature, for example, 100 C, that material can fail at 150. If it resists H2S at a pH of 5, it can fail at pH of 3, for example. So there is no material which resists H2S under all conditions. And just keep in mind that as the material is corrosion resistant, the cost of that material is more expensive. So when we are designing the material for application or selecting material for application, we consider the cost as well. So all these factors playing a role here. Hope this answers your question.
There's someone says, even if we have glass fiber.
Okay, so that's we are talking about the non-metallic here. Okay, the non-metallic, they do not corrode. However, they deteriorate. Okay, and this is not my area of specialty, but I'll answer you as according to my knowledge that even the non-metallic get affected by the H2S. I'm not sure about the fiberglass, but that's out of my specialty. Sorry for that. I cannot just give you a wrong information.
There is a question. In H2S event, instead of isolation protection, can we make a filtration protection in the outside contaminated airstream?
Your voice were breaking. What was that again? Can you repeat the question, please?
In H2S event, instead of isolation protection, can we make a filtration protection in the outside contaminated airstream?
Okay, so you want to filtrate the H2S out of the air, right?
Yes, I think.
Okay, that's what we are doing. It's the scrubber at the back of the building. It filtrates the H2S. So instead of the H2S going to the atmosphere, it filtrates, it holds the H2S. So it filtrate it and send the clean air to the atmosphere. So that's what we are doing. But we are not doing that inside the lab. The ventilation take the gas and send it to the scrubber out of the lab. And that scrubber filtrate the H2S.
Okay. Is there another question? I think we reached the end of this lecture. Thank you all for attending, and thanks for Engineer Ahmed.
Thank you for giving me this opportunity. It was a
We
pleasure
appreciate
talking to you. So thank you
let's
very
end.
much.
You're welcome.
Okay, thank you very much. Bye.
lecture.